So the goal of this next section is to introduce Hermitian operators and to define Hermitian operators, and also to take a particular quantum mechanical operator and to demonstrate that it is Hermitian. Before we do that, I'm going to first review integration by parts, because we'll use this in the proof for example, why the momentum operator is in fact Hermitian. So let me start by actually stating the definition for a Hermitian operator. So if an operator is Hermitian, then the following follows. Here's our complex conjugate of our wave function. Here's some operator A, dx. So if Hermitian, this is equal to the following expression, where now we have the complex conjugate of the operator operating on the complex conjugate of psi dx. So this ends up being a definition. So what we're going to do is I'm going to illustrate that the quantum mechanical operator for momentum is indeed Hermitian. So let me write down what our goal is next. So the question we're addressing is P sub x hat. So this operator, which we know is equal to minus I h bar di by dx, is that Hermitian. In this particular example, we're also going to set this up because we're going to say we're going to consider a wave function psi that goes to 0 when x goes to infinity. So what I'm now going to do is just quickly give an overview of integration by parts. So how do we do integration by parts? Well, so we're going to be considering an integral of two functions multiplied together. And before I do that, I'm going to draw on the product rule. So if we have a product rule that says we have two functions, f of x and g of x, and if we want to take the derivative of that product with respect to x, we of course know that that is equal to the derivative of f of x multiplied by g of x plus f of x multiplied by the derivative of g of x. So to consider integration by parts, first of all, what we're going to do is we've got this expression, so we know that to be true from the product rule. But what we're now going to do is take the antiderivative of this equation, in fact. And of course, the antiderivative of the left-hand side is simply we're going to leave ourselves with f of x, g of x. And that is going to be equal to, well, the antiderivative of f prime x g of x is equal to the integral of f of x g of x dx plus the integral of f of x g prime of x dx. So in the next slide, what I'm going to do is rearrange this, because in integration by parts, we're typically going to say, let's use this approach to find the integral of the second term on the right-hand side. Let's look at that in the next slide. So just rearranging this expression, I'm now going to solve for the second term on the right-hand side. So let's rewrite that over here. And that is equal to f of x, g of x. Now minus, so doing our algebraic rearrangement, the integral of f prime x, so the first derivative of f of x, g of x, dx. And what I want to do now is actually just jump into assigning some of these values, and you'll see where this ends up being important as we consider Hermitian operators. So in fact, what I'm going to do is I'm going to say that f of x in this case is going to be equal, I'm going to call that psi star, and I'm going to have g of x be equal to psi, and I'm going to plug these in to this expression. So when I do that, what do we end up with? We're going to end up with the integral of psi star, and now we have the first derivative of g of x dx, and all I'm doing here is just plugging this in to here. So we know that the derivative of psi star, so what I'm doing is plugging this in here, so I know the integral, also the derivative of psi in this case is just d psi by dx, and that's equal to psi star psi, and that's this function here, minus the integral of d psi star by dx multiplied by psi dx. So how does this help us? Okay, so if we, by the way, are applying our operator to, let's apply our operator to psi, for example, that would end up being minus I h bar d psi by dx, okay? And what we're going to do is at some point we're going to, because the Hermitian operator from the previous slide, by the way, let's have a quick look. Here's the operator from the previous slide. If we want to test whether something is Hermitian, we're going to end up doing these integrals, right? So we're gonna do these integrals. So this is why I'm doing the integration by parts. Okay, so what I ultimately want to do, and we'll see this shortly, is I want to take the integral, so I'm going to take the minus I h bar outside. I'm going to do an integral of psi star multiplied by the operator that's operating on psi. So I'm going to try and reproduce this left-hand side of the equation. And this is why it's relevant. So that ends up being psi star, and the operator now, I'm including this operator, which would be, that's this momentum operator, d psi by dx, and that, by the way, that's equivalent to the following expression, psi star p of x hat psi dx. Okay, so that's the left-hand side. So this is the left-hand side of the equation that allows us to define a Hermitian operator. So our job here is going to say, well, can we mathematically demonstrate that the left-hand side here that I've put in the red bubble here is equivalent mathematically to something that I'm going to ultimately pull from my integration by parts. That's where we're going. So in fact, if we think now about this expression, right? So let's go through this as if it's an integral. So this piece is equal to psi star psi, and with an integral, of course, in our particular case, we've got the limits of infinity and minus infinity in here, minus the integral of psi d psi star by dx. That's dx, and that's this piece written in here. So furthermore, I'm also going to say from the previous slide, since we know that psi goes to 0 as x goes to infinity, then we know that this piece in our integral in here will equal 0. So what we're going to end up with, let's put the whole expression in. So the expression at the bottom in red comes from integration by parts. We've got one piece that's very easy because it ends up being 0 based on our knowledge of the wave function. So what this ends up leaving us with is an expression here that I'm going to write on the next slide. And that is, putting the limits in now, psi star d psi by dx dx is equal to minus, put the limits in again, psi d psi star by dx dx. Okay, so this we know is true from our integration by parts approach. What I'm now going to do, by the way, let's multiply this by minus I h bar across the board. So this now becomes plus I h bar psi d psi star by dx dx. And we recognize again, kind of saying over and over again here now, that really what this is this psi star multiplied by the momentum operator, which operates on psi dx with those same limits. Okay, and we know from integration by parts that it's equal now to this term on the right hand side. Separately, I'm also going to point out that the complex conjugate of the momentum operator, which shows up in our definition for a Hermitian operator, right? So when we do a complex conjugate, every time we see an I in there, we change its sign to a minus. Every time we see a minus I, we change it to a plus. So effectively here, the complex conjugate of this quantum mechanical operator is simply I h bar. In this case, it would be di by dx, but since we're working with a function in terms of x, it's going to be d by dx. So what we can now recognize, by the way, is that we are, in fact, this I h bar d by dx is this underlined portion. So let me just clarify everything, and this is the final statement here. So what have I shown you? This is where we started. Okay, so this is our term from the right hand side in here of our definition of a Hermitian operator. So let's remind ourselves what that is. What would that be? Mathematically, as I've mentioned, we're going to plug in this operator in here, so it ends up being plus I h bar psi d by dx operating on psi star dx. And from the integration by parts piece, knowing that these two are equivalent, right? This we know is absolutely equal to minus I h bar over the limits from infinity to minus infinity psi star d psi by dx dx. And therefore QED, quod erat demonstratum, in other words, so yes, P sub x hat is Hermitian. Okay, so we used integration by parts to justify that our definition was indeed true for the operator for linear momentum in the x direction. So there's the proof that it is Hermitian. Why does it matter? Well, later on we're going to find in later chapters of the textbook, and when we look at more complicated systems, we're going to find that this particular principle that quantum mechanical operators are Hermitian is going to be quite important. So what I've done in this particular section is I've gone through and I've demonstrated how we can test if something is Hermitian or not, whether we can how we can test whether an operator is Hermitian or not. I've also reminded you of how to do integration by parts. And this is a topic that is a good derivation that I sometimes ask on exam questions. So make sure that this makes sense to you all before we move on to the next section. Okay, thanks for listening.